Thank you very much for the introduction and for the invitation. So I will try to tell you a little bit how we use machine learning and optimization in quantum chemistry. Right from the start, I should point out I'm a quantum chemist, so my expertise is quantum chemistry, certainly not machine learning and optimization. We are using those as tools, and the talk will be to show a little bit how these tools can help you in an applied field here in quantum chemistry. Let's start very basic. What is a theoretical chemist or a quantum chemist doing? Well, he's trying to investigate molecules or materials at the atomistic level, not by experiment, rather by using basic physical theories, classical mechanics, and quantum mechanics. I mean, here you have an example of a somewhat unusual molecule. It has these 5, 6, and 7 rings, and you can ask why does it form, what properties it has, and we usually do this in cooperation with experimental partners. And then we provide, for example, electronics properties of such materials. Or the other example is, it's quite fashionable now today, are two-dimensional materials. What you see here is a sheet of an iron bromide, well, one-dimensional, or I mean, it's just a few atoms thick on a gold surface. And if you look with an experiment, with a scanning tunneling microscopy, you see these holes. We can simulate this. And then we can ask the question, why do we have such holes? And they are interesting because they have special electronic properties, and you might use such materials for future molecular electronics. So these are typical questions we are asking. Often you want to know also about the dynamics. How do the atoms move, or how stable is this? And this is more what we are going to look here. But we are doing this using both quantum mechanics and classical mechanics. And then, of course, the expensive steps we want to avoid by using machine learning. But we first have to look a little bit, what are we doing in classical mechanics? So to speak, the classical example of classical mechanics is the movement of planets, or generally you have some particles in some entities. Here it's planets, and you know how this is done, maybe from school. You propagate Newton's equation. So first, what do we want to know from theory? In the case of classical mechanics, we want to know the position and the momentum, this is mass times velocity, of each particle or entity, here it's planets, at every time given a certain starting point. And we do this with Newton's law. You all know this from school. So mass times acceleration is the force. So this, you can also write it in the way, the derivative of the momentum. Momentum is mass times velocity. Velocity is the first derivative of the position with respect to the time. Acceleration is the next one. The second derivative, and the fourth depends on the position of the quantities you're interested in, here, the planets. In this case, this is very easy. This is the gravitational law. It's always two particles, I mean the distance or the mass, the product of the mass is divided by the distance square is the force. In general, we are looking at what's called conservative systems. So we consider the potential energy of, whoops, is it working? Of our system, and somehow, oh no, okay, it's a bit weak. Okay, so we have to take the negative of the derivative of the potential energy with respect to the coordinates, and this gives us the force. And this, I want you to remember this formula because we will use this later on. Okay, now let's briefly go back. What are the limits where classical mechanics work? There are two limits. The particles must not be too fast. If the speed of the particles comes close to the speed of light, then, so to speak, the mass becomes dependent on the speed. Then things become more complicated. We are not looking into this. And the other limit is if the particles are becoming very, very small, then classical mechanics is no longer working. What you then need is what's called quantum mechanics. Let's first look, what is the aim? What do we want from quantum mechanics? A simple system is a hydrogen atom. You have one nucleus and one electron. Let's assume the nucleus is infinitely heavy. Then we have only one particle. In a classical picture, it will circle around the nucleus. But you cannot, for principal reasons, ask the question, where is the electron at what time with what speed? Nature will not give you an answer to this question because classical mechanics is not working for such systems of that size. Instead, what you get is, or what is the basic quantity you're also calculating, is what's called a wave function. It's a function in space, in generally a complex valued wave function. And the wave function itself cannot be observed, but what you can do, let's see whether this again, oh no, it works. What you can do, you can take, so to speak, the product of the function times its complex conjugate, so you get the square of the magnitude. This is a positive quantity, and this gives you a probability distribution. It tells you the probability, in our example, of finding your electron or a probability density at that point. So if you multiply it by an infinitesimal volume, it gives you the probability that your electron is at this position or in this small cube, in this small volume. Okay, and then now how do you get this function, this wave function? You get it by solving what's called the stationary Schrödinger equation. This is, so to speak, the basic equation of quantum chemistry. It's a second-order partial differential equation. And how do you get the operator? That's called the Hamilton operator. This is, you start, you consider, this is, so to speak, if you start from classical mechanics, you write the energy of your system in terms of position and momentum. For example, in our single electron in a hydrogen atom, you could say, okay, let's first consider what would be the classical energy. Okay, it would be the kinetic energy, you all know from school, 1/2 of the mass times the velocity square, or otherwise the momentum square divided by the mass in 2. And then you have a potential energy. This would be here the Coulomb energy between the proton and the electron. And what you now do is, to come to the Hamilton operator, you leave the part on the spatial variable as it is, but the momentum you replace by the derivative minus I is the imaginary unit. This is Planck's constant times the derivative here. Now, if you're interested in the kinetic energy, that is the square of the momentum, you get the second derivative. And this is then, for example, the details here are not important. This is the Schrödinger equation for a molecule. And in each term, you can easily tell what it is. Here you have a second, this Nabla operator is a second derivative. So the second derivative with respect to x, y, and z. This is always the corresponding momentum operator square. And you have this, of course, for each particle, for each electron. Then you have the interaction, this is a simple Coulomb interaction between your nuclei and the electrons. So to speak, this is electrostatics, charge of the electron times charge of the atom divided by the distance. Okay. Here, what is missing, so to speak, you don't see this h bar, or you don't see a mass of the electron. This is simply because the first thing you do is you switch what's called atomic units. And in atomic units, the unit of mass is the mass of an electron. So it's 1. H bar, Planck's constant, is also 1. Also, the unit of charge is the unit of an electron. So it has -1. But the nucleus is the nuclear charge, so to speak, that you see. And okay, here is the distance of 2 electrons, and you could imagine that here you have the charge -1 times -1, so it's again a Coulomb interaction between all the electrons. Then you have the kinetic energy of the nuclei, and here now you see a mass, because the mass of the nuclei is not the one of an electron, it is much bigger, and this will be very important. And then you have the Coulomb interaction of the nuclei. Solving this equation is way too complicated. You can imagine a typical molecule, let's take 20 nuclei, a few hundred electrons. I mean, so you have here hundreds of coordinates. So this will not be possible. So the first thing is something, and that's important for what we are then doing, is what's called the Born-Oppenheimer approximation. And it comes from the fact that this is a big number. So in atomic units, for example, even if you have just one proton, which is the hydrogen nucleus, it's 1,800 in atomic unit, and usually you have bigger nuclei, so this is a huge number. So you could say, okay, let's assume the following model, that we have our nuclei at fixed position, they don't move for a second, and we solve first the electronic problem. And then we have the nuclei slowly compared to the electrons, of course, moving, and the electrons are always in equilibrium with the position of the nuclei. So then this, oops. No. Okay. Then this term drops out. This is just a constant because our nuclei are not moving, and we get what's called the electronic Schrödinger equation. It's now only things of the electrons, but of course, parametrically, our wave function depends on the position of the nuclei because they kind of generate the potential the electrons move in. Now, for the time being, let's assume that we somehow can solve this equation. I will come later. We cannot do it exactly. We do it approximately. But if we can solve it approximately, then we get the energy of the electrons in a certain nuclear configuration. And this gives us, I told you, if to propagate Newton's equation, you need, if it's a conservative system, you need the potential energy, and then from the derivative, you get the forces. And here our potential energy is given by the electronic energy as function of the nuclei plus the rather simple electrostatic interaction of the nuclei. So if we now want to do ab initio molecular dynamics, we will treat the nuclei again as classical particles with Newton's equation. This is well known how to propagate Newton's equation, like we propagate our solar system. I mean, people do this have been doing this for many, many years. It's very accurate. But the critical step is our forces are obtained. Okay, taking the derivative here is trivial, but we need to take the derivative of the energy of the electrons. That means in each time step, I mean, in propagation, you start from a certain configuration of states, then you take small times, propagate Newton's equation, and then you follow them how they are moving. But the forces in each step require to do a quantum chemical calculation, which is very, very expensive. So one can do this for systems that have a certain size, if they're not too big, but usually you want to do things that are faster. A well-established technique is, okay, that you say, okay, I have my molecule, and now I need the forces between them. The exact way is doing the electronic structure calculations, but this is expensive, so let's do something that's much, much cheaper. Let's assume that there are only simple model potentials between here. The simple thing is here, let's say this bond between those two, you say, okay, there's something like a spring in between. You may know Hooke's law, so it's a quadratic potential here, and if you take the derivative of this from a parabola, you get a linear force, so that's what you know from school. The further you pull on your spring between those, I mean, linearly you get a force pulling it back. And you can do this. You have other things here, like here. This is periodic, so you have something that's harmonic here. But then, if you do 120 degrees, you're back here. You have also long-term potentials. They have a bit different term, but you can, so to speak, implement those, and this can be done very fast. And you know this maybe from biology. They do huge macromolecules, whole enzymes. They can study with this. But you can immediately see what is the problem, or what is a thing you need. You need well-defined bonds here. And in chemistry, we typically try to break bonds. We want to do reactions. But in such a potential, you would never get, I mean, this is an ideal, so to speak, spring between them. It would work forever. In reality, you know what happens. If you have a spring, you pull and pull, okay, then you have Hooke's law, but at some point, your spring is going to break. And this is exactly what is happening in a molecule. But this you cannot describe by this. Also, you have situations, for example, we will later look at liquid metals where you don't have well-defined bonds. Then this is not working. So one thing is that you really then do ab initio MD, that at each step you solve the electronic problem. You can do this, but I mean here in these examples, you can do it up to something. DFT is a way, that means density functional theory is one way how you solve the electronic problem, and you can do it maybe for 64 atoms, and you can 2,000 steps in your MD, and it takes you in some computer setup 8 hours. But you're more interested in something like this, where you're 40,000 atoms, and you want to do it not 2,000, you wanted 100,000 steps, and you still can do it in 10 hours, but then you cannot use the force fields I was describing before. You need somehow to implement the information you would get from a quantum chemical calculation in a machine learning way, and this is what we are going to look at now as one example of machine learning. So let's briefly look again why we are interested in this. Okay, in this machine learning interatomic potentials, we abandon the physical motivated model. We are not saying this is behaving like a spring, has an harmonic potential. We make no assumption at all. We just, okay, it can be whatever it wants to be. We somehow have some input and some output. The input will be the geometry, the outcome will be the energy and the forces. This is what we need to propagate Newton's equation. And what we will assume that something that's geometrically similar will have also similar forces and energies. This is usually, I mean, nature doesn't make jumps, so in that sense, this is probably true. The great thing is arbitrary systems can be described. You don't need any predefined bond orders, and the accuracy is limited only by the amount of input data. If you have enough training data, then you can describe it more and more accurate. The thing that's a bit, okay, it's a bit slower than traditional force fields, but it's still fast enough with modern computers. But it has an unfavorable scaling with the number of elements. And here you have to be careful what's meant. The methods usually scale linear with the system size. So once you have trained them and you go to bigger systems, okay, if the system is twice as large, then you need twice the computational power. But this is for quantum chemistry, that's a very favorable scaling. Typically the electronic structure method, they have something that we call n cube, n4 or so scaling. So if you double your system size, fast methods then go doubling the system size means 2 to the 3, 8 times, but you have accurate method scale like n to the 7. So if you double your system size, you get 2 to the 7 additional amount of computational time, which then is very expensive. But however, what does not favorably scale is the training, because if you increase the number of elements, you have much more possible arrangements, and this number explodes, and this then makes, we will see this in more detail in a second, will make the training very difficult, at some point impossible. So there are many different flavors of machine learning in these MD simulations. We will concentrate on one, that's so-called kernel learning. It is something that's in one of the professional programs that are distributed. You can buy them, or if you're in the developers community, you might get them for free. This is called Vienna Ab Initio Simulation Package. And the first idea is, okay, our energy is the sum of individual energies of atoms. This is already good, because this means it's linear with the number of atoms. On the other hand, this is already a certain assumption. And then you say the energy here of each atom depends on its environment. So the first thing you do, you make a certain sphere around your atom. You then go atom by atom, and each atom contributes to the energy. And if you take the derivative, I will always talk about the energy, but you learn actually also the gradients, the forces at the same time. But let's, for the sake of simplicity, concentrate on the energy. Okay, and we say the energy depends only on the configuration of other atoms in a certain distance. Of course, you have to make this is an approximation. The larger you make the sphere, well, the better it becomes. But of course, you have to keep things computationally feasible. It should not become too big. And what you then do is first, you need a more or less large set of reference environments where you know the the contributions to the energy, or we'll see how we do this, and then you simply compare. You propagate, you have a certain arrangement, and then for each atom you look, you compare it with the reference environments. The first thing is, how can you do this? If you have, so to speak, really exact positions here, you will never hit exactly the same position. So the first thing is, what you do is, you have to broaden this. You put, instead of saying, I have here the position, you put a Gaussian function. So this gives you probability distribution, where you say you have your atoms, and then you can compare quite well. If you have, so to speak, if you compare the two, they are not very similar. You have Gaussian functions on each position here, on each here, and then you simply take the product and integrate it. If they're on top of each other, the integral will be big. If they're in a way that there is no overlap, it will be zero, then there will be a relatively few similarity. And this is in principle feasible, but you will immediately see that this is too much information, because if you rotate this, I mean, if you just rotate the arrangement, it should have the same contribution to the energy. So you have to reduce your information, so you need descriptors that have a reduced information, but still the information you want. So what you simply do is, you calculate what's called a radial distribution function. So you broaden this by Gaussian functions, and then you integrate over a surface, and you take only the probability integrated over the sphere of a certain distance. This gives you quantities like this. This is a radial distribution. It gives you the probability to finding in a certain distance another atom. Okay, but if you do this, then you have reduced the energy or the descriptor too much, because if you now would leave the distances but just change the angle here, you would get the same probability distribution, but the energy certainly would be different if you put two atoms together here. So you have another type of descriptor that gives you, so to speak, the probability. This is your reference atom I, that you have one atom at the distance r, another at the distance s, and you have angle, a certain angle theta between them. And this is the two type of descriptors we use. And then let's stick with the radial distribution functions down here. The blue line is, so to speak, the distribution of something you want to test, and the red and the green are two references. Then you could take the integral and see, do they overlap or not. This is doable, but it's not very computationally not very efficient. So the first thing you do with these functions, you develop them in also normalized Gaussian functions. Then you can simply take the coefficients and take the scalar product of the coefficients of the geometry you want to analyze times the one of your reference calculations. And if you do this and you sum these scalar products up, no, I think it doesn't work anymore, then this is what this kernel is doing. This kernel, so to speak, you have xi are all the coordinates or the descriptors in a vector summarized, and xib are all your reference geometries. You take the scalar product, and then you get a measure for how close they are or not. And then what you do is you multiply these measures of the closeness times some weights wib, and this gives you the energy. And these w's are the quantities you have to learn. So we will now do in a clever way. Of course you could do, if you have all these test systems, you can try to get back the reference energies from the quantum chemical calculations for your reference systems. For your reference systems, you have to do these expensive quantum chemical calculations. And then you could do it in a least square sense to optimize the W's. We use a Bayesian linear regression. The advantage of this is you not only get in a certain way optimal coefficients, you also get an uncertainty measurement, so you know how reliable this is. And the great thing, but this we can see on the next.
So beta 2 and beta 3 are constant, and you can learn
No, these are weighting factors. You can weight whether you want the angular distribution or the radial distributions more, but this is something, yeah, you also use in your optimization. So, and you do this, you start with an ab initio MD here, a lot of time steps that are these blue, the beginning, the blue region, and because you need to generate some structures. Then you do a first force field optimization. You machine learn your omegas, your quantities. You have a first force field with a certain accuracy measure. And then you switch to this force field and let it run. And the nice thing with this Bayesian linear regression is you also, if you do a step using only your force field, you can, if you get the output of it, you can estimate its probability or its accuracy. So you have a descriptor during the cheap and efficient usage of the force fields. At each point you can nevertheless say statistically this is a structure, this is well described or not well described. And then after a while you might enter a region of your system which was not described well, then your Bayesian error tells you now you're no longer on safe ground. Then you switch back to the machine, to the ab initio MD. You move on up until you again reach a region that is not well explored. And of course, after a while, you hopefully are in a region where your force field is great. And then you say, okay, my force field is good. Then I take it, and then you can go to much bigger system and use it. Okay. This ran out of battery. Okay, so let's now consider a brief example where we want to use it. This is called SCALMS. This stands for Supported Catalytically Aqueous Liquid Metal Solutions. So our experimental partners, what they want to do is they have some support, a silica. You might, if you buy some electric device, you sometimes have some white powder, I mean, in some small bags. This is silica. And you can put on these, and it's a porous material, you put very small gallium droplets with some active metal nickel here, and at the reaction temperatures, in this case, you want to make out of two ethene molecules something that's called butadiene, a butene molecule. So out of two C2 units, you want to do a C4 unit. Chemical industry is doing this, and you need a catalyst that helps you doing this reaction. And this is this liquid metal with this nickel inside. So what they wanted from us, that we simulate the liquid gallium with some molecules, with some active molecules in there. And this is what we did. You do some models. In this case, what you do is, what you here see is really the cell we are simulating, but the cell is automatically has periodic boundary conditions, so it goes to the left and the right, back and front infinitely often. So it's a slab of material which kind of models the surface. I mean, you have two surfaces here of our material. And then the first thing is you can have different learning strategies. For example, you learn linear heating. You start at low temperatures with you begin. This is small enough that you still can do an ab initio MD for a certain type. So you can do the expensive steps. For this you use for learning. You heat it up, or you heat at a constant high heat. So one is better than the others. I will not go into the details here. And then you can do also, once you have learned your system, you can also go to larger systems like those you see here. For example, you can then from this calculate the diffusion rate in there. This is something you can measure. If you go to this is done with neutron scattering, so you have to go to a reactor where you have neutrons, and then you can calculate or can measure how the diffusion of nickel or of gallium in the presence of nickel works. And this is something the experimentalists want to know. And we can, for example, then simulate this, and we can get additional information. The experimentalists, for example, can only get an average diffusion coefficient for gallium and nickel. We can calculate them individually, so we can give them extra information. And these are typical things that we are interested in. For example, what you want to know is simply the distribution of elements. This here is a system where you have gallium and platinum. And in your chemical reactor, you want the platinum to do something with your gas phase molecules. So, well, it will only work if the platinum is at often enough at the surface of your catalyst. So this is something we can calculate. We run these simulations, and then we consider the distribution. This is where they have this orange line. This is a cut through, so to speak, at the left and the right. This is the surface of the system, and you can see the probability of finding a gallium. Okay, it's if you're outside the system, that's to the left and to the right of the orange line, then you're outside. I mean, we have this slab here, and you cut through it, and you say the probability to find platinum. Well, far above the surface and below, there is nothing. And then, okay, you have some oscillation, and in the middle, it's more or less, so to speak, that's the density of liquid platinum. Oh, sorry, I have to kill this. I forgot to put it on. Okay, so now we will not be disturbed. But the interesting part now is where is the platinum? And this is the blue distribution. And here you see that the blue distribution is such that there's very rarely any platinum at the surface, which is not that great for catalysis. You can calculate the concentration of platinum in the first layer. It's well below 1%, but in the second layer you have at least 1%, and you can relate this now to experiment. Here what you see is there is different of these systems, yeah, gallium with platinum, indium with platinum, and you see in the measurement the catalytic activity, and you can try to relate it to the surface concentration, and it works in many cases. The one, this SNP2, has the highest platinum concentration, also the highest catalytic activity. But if you look above the indium platinum, you also have a pretty high surface concentration, but a very poor catalytic activity. This tells you that this is the concentration at the surface is only one point to look at. The other is something where you have to look at the electronic structure. You need that the electronic structures are energetically close, otherwise it is not working, and this is not, not the case in this indium platinum. But here we are only concerned with how you can so to speak, simulate the distribution of the phases here. What you also can see that these force fields, you have to be very careful with them, that you can see a little bit here. If you look at the left distribution, there is the SN, the tin in there. And if you see the distribution, here it compares the distribution calculated with an ab initio MD, an expensive calculation with doing the forces by quantum mechanical works, or with our machine learned force field. And it's not completely off, but if you look at the gray lines, at the very left, you find apart from the slab, a finite probability to finding tin atoms. This means that during your simulations, atoms went out of the surface into the vacuum. This is something which will not happen because these elements, the vapor pressure is extremely low. They do not evaporate at these temperatures of a few hundred centigrade. So something is wrong with the force field, and you can cure this if you select here the reference configurations in a more clever way. I don't have the time to go into details. If you do this and go to the picture on the right, you see, for example, the dashed gray line and the solid gray line, they coincident better here, and you no longer have atoms that go out of the system. And this tells you something that's generally true in these machine-learned force fields, or generally in machine learning. I mean, it works as long as you're within the area which you have learned before. In the moment you go outside this area here, if an atom for some reason in your simulation becomes a bit too far away from the surface, then this is a configuration that was not in the learning process, and then it doesn't know what to do, then it just runs away. So you have to make sure that all the information you need is learned. On the other hand, if you do this, then it's very nice. Now look at this here. I mean, it takes a bit, and now you see something happens here. Before it was wild, now it becomes slowly more and more ordered, so it becomes slowly crystalline. This is a gallium, liquid gallium platinum at a certain concentration, and what you can observe here is a crystallization. It forms what's called an intermetallic compound. And this, nowhere in our learning we had intermetallic compounds in there. We just learned in liquid systems all necessary environments. But apparently the information of all these environments also is enough, or that's what you need, or that is what also can drive a phase transition. So if you learn it good, then it also can tell you the simulation some things you would maybe not expect. We did not expect to see this. This just happened. And it's typically very difficult to describe phase transitions, and that tells you here the machine learned force field obviously is good enough to do this, because afterwards, once we had these phases, okay, now it's gone again, we compared it to well-known phases, and it is exactly a phase that is well-known, and the experimentalists then also can observe it with X-ray diffraction or other means in a transition electron microscope. You can observe this, and we now have collaborations with them to try to explain some. For them it's not, they get some information, but to know is it really the phase I want, so to speak, it's helpful if you have also theory, and we now know if we have good enough learned machine learned force fields, we can do these relatively or sensitive steps to do this. And this, so to speak, shows you, so to speak, a strength. On the other hand, the transparency before showed you a weakness or a point that you have to be very careful that you're training. I mean, this is not black box. I mean, there can be effects that are unphysical, and then it typically tells you your training was not good enough. So, but then on the other hand, it can give you nice information. So if we summarize this, if you have a good enough machine learned force field, you can create the DFT, that is a quantum mechanically data, without underlying physical assumptions. So you can do it quite unbiased. Often in physical models, you say, I want to have this effect, and I can describe it with this, and then you put this into your model. This you don't need to do. I mean, you just learn whatever your basic theory gives you. In this case, quantum mechanics should give you. And if you learn it good enough, you get more or less the same results. Okay, it's said here, and it relies heavily on the learning process. And yeah, if you do it you can do much larger systems and longer time scales, which you cannot do usually. Here in this specific area of these calms, this liquid metal quantities, you can calculate diffusions, you can calculate the elementary density distributions and radial distribution functions, all sorts of quantities, or even the observation of intermetallic phases. I don't know. This is the main part of the talk, and I think it's supposed to be 45 minutes. Then I would stop. Otherwise, I would have another 10, 15 minutes. A bit. Okay, then I move on.
So, can I ask you something?
Sure.
So what happens if these machine learning methodologies that you were able to implement successfully at such a high scale and discover phenomena that, on the other hand, are known experimentally? What happens if you apply them for smaller scale models that you know how to handle by more classical tools?
Well, then usually this is what...
Discover new things, or you just observe?
Well, we usually do this, no, then usually we get back, this is what we typically, let's see, here, this is typically a test for us. I mean, the dashed line is, so to speak, what we get from a standard ab initio MD with electronic structure calculations, and then we run the same thing with the machine learned force fields. And here, what we want that the curves agree. Here they don't do that well. Here they do better because our training was better. And that's what we usually do. But we usually don't learn more, except in the sense if we look at the same model, which then is naturally a small one, because with the expensive method we can only treat the small one, we can at least take longer times. And this sometimes gives you more information. For example, that in the expensive calculation, for example, if you want to know whether you can get hydrogen, this is what we are looking at in the moment, if you can get hydrogen into a liquid gallium metal, then with the standard methods, the time you can do this is that short, you don't see enough. But we can now, with the machine learned, we can do it 100 or 1,000 times longer, coming to macroscopic time scales, and we can see some diffusion processes which we cannot see. But I would not say that we would see that we could see phenomena. This then would be an artifact if we would see a phenomenon in the machine learned which we principally cannot see in the more exact calculations. Then we have learned something into which we should not have learned into. So this is something we don't want. Okay, now let's come to something that's not really machine learning. That's something what you do very often in quantum chemistry. You do some optimization at some point to make the electronic structure problem simpler. So now we are back to how do we solve the Schrödinger equation. This is, you have seen the formula above. This is the Hamiltonian operator. So the Schrödinger equation is the second line. You have an operator acting on your mostly we are interested in the wave function of the ground state. And you have these terms, the kinetic energy, the interaction energy with the nuclei, the electrostatic, and the electron-electron interaction. And there's a theorem that's called Hohenberg-Kohn theorem. And for this, you need a quantity which is very condensed information. I told you if you take this wave function, it has as many variables as your system has, so to speak. Each particle has 3 variables, x, y, and z. So if you have a molecule with 100 electrons, which is not a big molecule, you have 300 variables. And if you take this wave function times its complex conjugate, then you get the probability density of finding electron 1 here, electron 2 here, 3 here, and so on. This is a very complicated information, but if you're now interested in the probability of finding electron 1 here, then at first you get a conditional probability, namely finding electron 1 here, while 2 is here, 3 is here, but you can integrate over all the other probabilities, then you simply get the probability of finding electron 1 at this position. And we will look at this later. All the electrons are indistinguishable. That's one of the requirements of the wave function. So if you have the probability of 1 electron, it's the same as of each of the other electrons. So if you multiply this probability by the number of particles, you get simply the probability at a certain, or the probability density to find an electron at a certain position. And this is a much more condensed quantity. You can measure this actually. And this is what's called here, for if it's the ground state electron density. And there's something that's called the Hohenberg-Kohn theorem. It tells you the ground state electron density determines the Hamiltonian operator, and thus, via the Schrödinger equation, all properties. And a trick now to work with electronic systems is, what makes the Schrödinger equation is difficult, if you look at the Hamiltonian operator, is the last term. Because the last term couples each electron to each other electron. The term before is the interaction with the nuclei, but the nuclei in our approximation are fixed. So they are just they span an external potential. The first 2 terms, each electron only sees itself, not the rest. And the difficult thing is the coupling of all the electrons. So you do something that physicists like to do. You throw away, I mean, it's something that not necessarily works in life, so you just ignore what is the problem. But here it works for a while. So we introduce a model system where we say, okay, it should have the same electron density as our complicated system, but it's of artificial non-interacting electrons. They're called cone-sham electrons because Kohn and Sham were introducing this model. And if you now consider the Schrödinger equation of such an artificial system, it only has a kinetic energy and some effective potentials where the electrons move in. But now the differential equation, at first it's all, again, for all the particles, but they are no longer coupled. So it decouples in simple differential equations for just one particle. So you only have x, y, and z coordinate of an individual electron. And this you can easily solve by known techniques on a computer. And then, so to speak, the solution of the complete non-interacting, it's still the model system, of all is simply the product of the one electron solutions. But you cannot take a simple, mathematically you can take any product, but what you need to take into account is that the electrons of a system are indistinguishable, and there is something, the Pauli principle, if you interchange two coordinates, the wave function has to go into its negative, because electrons are fermions, they have a half-integer spin, other particles are bosons, then it has to be +1. And this you can do by a simple trick. You take a product and then you take all permutations and always change the sign if you make one interchange, and this is mathematically nothing else if you write it in this form as a matrix and you take the determinant. So these wave functions are called Slater determinants. Those we have some access to, we can calculate, but of course we are not interested in the energy of our artificial system. In the end we want our true system. So what we are doing is we define something that's the correlation energy. These brackets are abbreviations for integrals. And if you look at the first integral here, this is, you have your Hamiltonian operator, the Schrödinger equation, acting on its eigenstate. So you simply get the energy times the eigenstate. The energy is a number. You can take it out of the integral. And then you get the integral of the wave function times itself, which has to be 1, because the product is a probability distribution, but if you integrate all probabilities, there has to be 1, because the system has to be in some of its configurations. This is, by the way, a very important point in quantum mechanics. If you solve the Schrödinger equation, you need to make boundary conditions such that the square of your wave function, or the product with this complex conjugate, is integrable. And this, at the beginning you get much more solutions, but you have to throw away most of them because they don't obey the boundary condition, and that is what makes the quantization. That's why at least the lowest solutions are numerable, and you have a ground state, an excited, and another state. So this is very, very to the heart of quantum mechanics. But okay, so you have the first integral is the exact energy. In the second one, this expectation value, this integral gives you the energy of our artificial system. This we can calculate, but it's not the quantity we're interested in. And the difference is what's called the correlation energy. And this, and a lot of what quantum chemistry is doing, or has been doing over the last 50 years, is trying to get efficient, approximate formulas to calculate this correlation energy, as accurate as possible with computational effort that is still manageable. And one of these formulas, and the details are not at all important, is the one you have here, where you have, so to speak, this an integral, and you have these sigmas, and those you can get basically from the orbitals, from the solution of the one electron equation. So let's assume we can get the quantities we get in there, then this is a certain approximation. It's called the random phase approximation. And then a thing, what we were, for example, are doing as research, we want to correct this, make it better, and we do this in a simple way. We take the expression and add a correction function. This you can derive from physics, why this makes sense. And you have two possibilities. You could make physical approximations for this function, somehow find something that improves it, or you do optimization. You say, okay, let's take a test set, for example, chemical reactions. A plus B gives C and D. We do this for a few thousand reactions. Those we have to calculate with very expensive quantum chemistry methods, which maybe cost a lot of computer time. And then we try to optimize this function such that we get, so to speak, this by this RP corrected random phase approximation formula, which is much cheaper to evaluate. And this works. We do it very, very simple. We take just a number of splines, and then we optimize the spline parameters with these, yeah, it's something, I think, 20,000 reactions. And then we can calculate how accurate are we. And the orange part was our original, the simple approximations we started from. And then we have this, what we call sigma function. This is this correction function. And then you see the error distribution is much narrower. So we are closer to what we want. And I mean, the units are a bit weird units that are units that chemists use. That's kcal. I mean, you know perhaps kcal, it's on your milk or whatever. You can see how many kcal it has. So this is a typical unit you use in chemistry to calculate reaction energies, and you would like to have your reaction something in the order of 1 or 2 kcal per mole. Mole is a certain amount, Avogadro's number of molecules, 6 times to 10 to the 23. And you can see you can improve things. And this is a general theme in quantum chemistry, that you have your theories and that you work on to improve your theory and get approximations, but typically the methods that are used are often those which at one point makes a step that some quantities are optimized with reference data, because the point is always the same. Is, I mean, in principle, you know how you could solve the Schrödinger equation exactly, but you can also easily check that this will go up to molecules with maybe 6, 7, at most 10 electrons. And even if our computers, the computational time increases exponentially, even if our computers are 100 times faster, then maybe instead of 10 electron molecules, you can treat molecules with 11 electrons, but you're interested in molecules with hundreds or thousands of electrons. So there's no way that the computers will ever be fast enough that you can do a brute force solution. Actually, people with quantum computers, they believe that they have a better scaling. So that's, okay, I'm not into that business, but they have some hope that at some point, if they have stable quantum computers, that quantum chemistry would be a great field of application. Well, we'll see whether this will work out. But at the time being, this is not the case. So you need some approximations. And the point is, there are different, some say, I don't want to do any machine learning or optimization. I just want to invent clever approximations. This leads you to a certain, up to some point. But in practice, usually if you do clever optimizations at physically well-defined points, this brings you further. Okay, that was basically what I wanted to tell you. And yeah, if you have any questions, let me know.
Really exciting. So we have time for questions. Yes, Julia, please.
Have you done also parameter estimation to understand, for example, in the change of phase, what parameter caused at a certain time a certain type of transition?
Not in the sense that we would look, I mean, the quantity that we optimized, let's see if we go back to this. Here are these omegas, but they already at a level where you cannot really interpret much physically anymore. So what we, of course, we can, what we do if we do these simulations, we observe all sorts of quantities. If you have these trajectories, you can analyze which atoms are close to each other, or are there any clusters, things like this, but not an analysis from the parameters that are optimized here I mean, these are thousands of, I mean, typically for each element you have a few thousand environments. If you have several elements, you can have I mean 10,000 or something of these omegas. And there's actually, I would not know, at least maybe there are more sophisticated measures than to get something out of them. But this is not something we have done. Yeah.
I assume, like from what I understood, there's like a phase in which you have a model that you trust and you gather data, and then you have a machine learning model that you want to train with this data. Do you really gain a lot from doing this on the fly, like compared to doing this data acquisition first and then training afterwards?
Yes, I mean, this on-the-fly learning is the part of the generation. Afterwards, in your application, you typically no longer switch back. You can't do it, because if you have a system with 40,000 atoms, you cannot do a switch back to the complicated electronic structure calculation. So then you trust it, but even the learning is much faster. You could, of course, say, I just run it for a while, and then I hope I have enough data, that's it. But in this way, so to speak, the system then can do these efficient machine-learned steps, and you can kind of explore more of your space. Otherwise, you might miss something. You can, of course, you can say, I run it 100,000 steps, and then I'm happy, and then I learn my force field. But it may be that your system has not come to certain configurations in these 100,000 steps. I think in one, yeah, this is what you see here. If you would run a certain time, then maybe you would never come over this barrier and you would stick in here. But if you run it, then in these red areas, they are cheap. They don't cost you anything. So you can, maybe this is not, maybe one should now have here something where for a long time it's red, and then at some point it switches back. That's the point when you went over this hill. So in that sense, it's a more efficient learning. But in principle, you also could learn it differently.
I see, but this is always for a size of the molecules that the A, M, and D can work, right?
Yes, yeah, the learning has to be the size that, if necessary, you have to be able to switch back to the ab initio. This is clear. So you can also do tricks like, yeah, that you not simply, let's say we have these surface slabs. Of course, you know maybe a problem is sometimes atoms run away. Well, then maybe you start your system with a slab and you put some atoms in the gas phase, then they just will go by, they have some momentum in the beginning, then they will move into, and then you have exactly those configurations which, if you reverse the time, would be where they go out. So there's a lot of thinking about how you do the model to do the training, and that's important, because otherwise you get all sorts of artifacts otherwise during running these simulations. That's why it takes a certain time and experience. You cannot just say, okay, I have this machinery, I do it with this system, and now I do the next, and it has to work. I mean, this is...
That evolved in time. That's my first question. I mean, how standard is used is stationary model? The second one is, do you think that this kind of techniques can be applied for the time evolved?
This is the question, basically, whether you do this, what's called Born-Oppenheimer separation, that you do your nuclei classically and the electronic, only the electronic part quantum mechanically. That's often a good approximation, not always, and what people are doing sometimes is really they propagate the complete Schrödinger equation, including the nuclei. But this you can do only for very, very small systems. Another thing, but you have to distinguish. This is if you also want to treat the nuclei and you want to have some movement. You also could say, I stick with the Born-Oppenheimer description, I want to calculate the time evolution of my electrons. You could solve the time-dependent Schrödinger equation for this. But typically in chemistry, you're interested in the stationary states. But if you now, for example, shine light on it, you have transitions from one state to the other. Usually, you still do this in a picture with stationary states, that you take the states and you calculate from the states the transition probability. But you could also do it that you really propagate the electrons. This is done, and this is interesting in the moment you have not simply, well, light in what's called the dipole approximation, but if, so to speak, you have a strong laser pulse and the shape of the laser pulse has an impact on how the electrons are changed. Then you would do it by a real-time propagation of the time-dependent Schrödinger equation. This is a field that is done to a certain amount in the community. It's a bit a special area where it's done, but it's doable, and yeah.
So in your simulations, when you show these configurations vibrating very rapidly, what is the time evolution we see over there? This is a static configuration that we are learning, and therefore you are showing how the computer step by step is...
Yeah, but what you learn is you have these many configurations that come, but you learn not only the energy. You actually, I showed always the energy, but you learn also the forces, because this is what you need to propagate Newton's equation. So in the end, we do a propagation of Newton's equation if we do this, because we treat the nuclei classically, and then we do averaging over long trajectories. What is the probability of finding particles or atoms here or here? We can even, if we do learn it good enough, we can try to observe reactions. That, for example, we start with a small cluster of atoms that are catalytically active, and you have a molecule that should react, and then we observe how it comes, does some reaction, goes back to the gas phase. We can do this, not exactly with this model. We use a different model for this, because in those cases you have many elements and this is not working that well for that. But it's doable, and then you can simply observe things which in static calculations you cannot, and you don't. In a static, of course you can say, okay, I have this cluster, I calculate by hand some geometries and hope, but then you have to choose by hand, because this is a nice thing here. You let it run, and you can have it run for a long time, and then something can happen, like this phase transition. It can also happen that it makes some reaction, which probably you know it should do, but you can see, is it doing this or not by itself? And in the other case, if you try some things and it doesn't work, you never know, but maybe you haven't tried the right geometries. But here, if your system runs automatically long enough, then you can be at least more certain that it will find what you want to find. So, in that sense, you get more information.
Maybe a second question is not a very original one, but I see that the machine learning method that you're using is quadratic kernels, basically. So why this choice? Why not neural networks?
Oh, you can find in the literature, people are using all sorts of things, but for the properties we were interested here for these liquid metals, first it was available in this program, so we had a basis to start from, and it's working very well for those problems. We have other problems, as the one I just was mentioning, where from the gas phase we make reactions. There, this model in principle could work, but you would have to learn too much geometries, and then it explodes from the learning effort. And actually, it's not only the time, it's only you have to store all this information, and then you run out of memory on your computer. So you have to probably choose for certain types of problem, certain types of machine learning methods. And there's a lot around. This was just one example. It typically is done, you do a mean field calculation, And after you've done this, you get a correction, this correlation energy, by this random phase approximation. So it typically improves over the self-consistent field method which you have before. But it's a stepwise thing. You first do the mean field calculation, and afterwards then you do this random phase approximation to improve the accuracy of your calculation.
Other questions or comments? Okay, if not, thank you again, Andreas,
Okay.